Welcome, AP students. Today we're going to begin our Unit 3 review. So it is Intermolecular Forces and Property. You'll see a little bit of repeat from the previous two units, but we're going to build in this section a little bit more advanced chemistry. Within this virtual lesson, I am going to work several example problems. So Unit 3 will be broken up into Part A and Part B. So today you're going to be viewing Part A. Tomorrow I'll record another virtual lesson and I will post that on Tuesday for you. So that way you will have all of the resources needed for the completion of the AP Classroom Unit 3 quiz that I have upcoming due on Wednesday evening, and then Thursday is our Moodle test for Units 1, 2, and 3. It's a 30-question over the key concepts that are specifically the AP exam style multiple choice. So I do not have for Moodle free response, but these specific multiple choice I picked that they cover the concepts that are in the AP locked type questions that are supposed to be on the exam. So anyways, let's go ahead and get started. So intermolecular forces and properties. So we looked at a slide very similar to this last week, but you have several types of intermolecular forces, that is between other molecules. So let's start at the strongest one. Here is ion dipole. And that is an ionic bond, and that is in water, basically. That is a great example of it. That ionic compound is split apart by the dipole of water. So that's a very strong force that is happening to break apart a compound that has a really high melting point. So just think of it in that light. So the next one would be hydrogen bonding. Remember, hydrogen bonding can only occur between nitrogens bonded to H, oxygens bonded to H, or fluoride bonded to H. So there you have NONH, and it has to have that bond. And remember how it's operating. It's attracting to the unshared pair of electrons on either the nitrogen, the oxygen, or the fluorine. Then we have dipole, and we already knew what a dipole is. We have some slight positive and slight negative sides of an non-uniform molecule. Remember, if you have something like methane or carbon tetrachloride, that is tetrahedral, so any of the charges would balance out, but this is off of an asymmetrical, it's not symmetrical. And then you have these slight positive, and then you can have attractions, and those can be fairly strong, as you can see on the chart. Then you have dipole-induced dipole. That would be the interactions of a dipole with a non-polar molecule causing a shift in electrons to have some attractions. And then we have the London dispersion, or just as we call them, dispersion forces. And remember, that is typically between large molecules. It's in all molecules, but it has the greatest effect on a large molecule. So the movement of these electrons can cause momentary attractions and can predict why some large molecules are solids and liquids and gases based on these London dispersion forces. Next thing here, we have the rate of vaporization versus the strength of the intermolecular force. So we have three molecules we're going to look at here, and then we're going to look at specifically the structure of them. So let's look at the structure, which has a high vapor pressure. So here's a Lewis diagram. So let's just quickly label them here. So here we have our water. Here we have our acetone, and over here we have our ethanol. So just by looking at these Lewis structures, right away you notice a hydrogen bonding right here. You see a hydrogen bonding right there. So that right away should tell you that those two molecules have hydrogen bonding. So their vapor pressure has to be somewhat low. It's not going to be extremely high. When you look at the size, this is a compact molecule when you talk about water, compact molecule. And obviously it's polar as well. When you look over here at ethanol, ethanol is a little larger of a molecule. It has a non-polar end, and it has a polar end, and it has hydrogen bonding that's going to take place. So just by looking at that, you will realize that that is going to be a little bit higher vapor pressure than what water would have, just based on those criteria that I just said. And when you look at acetone here, you do not have hydrogen bonding. The hydrogens are bonded to the carbon here and to the carbon here, and you just have a carbon double bonded to oxygen. So that's not going to produce a hydrogen bond. So if you look at this, and we're just going to call this out at 25 degrees Celsius. So if we sit at 25 degrees Celsius, the vapor pressure of water is basically 0.0313 atmospheres. If you talk about ethanol, it's 0.0587 atmospheres. You can see by looking at that, slightly higher, but not a tremendous amount, almost double, but it's still quite low. And then you come over here to acetone, it's 0.296 atmospheres. So what does that all mean? That means the vapor pressure is high, which means if you spilt that, so say you had a bottle of acetone water and ethanol, and you poured them out on a table, very, very quickly, acetone would be gone. So that would be gone first, and it would go pretty quickly. The next one to evaporate would be ethanol, and then lastly, you would be left with water kind of hanging around there. If you relate the vapor pressure to the boiling point, let's do that for a second here. Water, we know that water is 100 degrees Celsius. That's its boiling point. If we look at ethanol, we could actually separate, because ethanol would dissolve in water, we could actually separate that based on its boiling point, because its boiling point is 78.3 degrees Celsius. So we have a vapor pressure of water that's very low and a very high boiling point. We have a moderate vapor pressure, and we have a relatively high boiling point. And if we look over here at acetone, its boiling point is 56.5 degrees Celsius. So with that now, we have a high vapor pressure and a low boiling point. So that's the correlation between those. So if we look at what forces are taking place inside there, here on acetone, acetone is dipole, and there's London dispersions because it is a polar molecule. You probably noticed that when we look back on this right here. It is polar. It has a definite polar area with that slight negative up here, and then you're going to have the slight positive right here. So it is a polar. So dipole, and London dispersions. Ethanol has the hydrogen bonding like we talk about, dipole, and London dispersion. And water, we know water's hydrogen bonding dipole because it's a polar molecule, and it also has London dispersion forces. All right, so now let's look at intermolecular forces and physical properties. The boiling point increases with increase in the strength of the intermolecular forces. So If you have strong attraction, that means your boiling point is going to be high. Vapor pressure. With increased strength, your vapor pressure is going to be low. You're going to have a low vapor pressure. Vapor pressure decreases with increase in its attractions. And then the melting point, with increased strength, the melting point increases. So strong attractions, think of a solid, strong attractions, their melting point is typically high. So those are intermolecular forces and some physical properties. Here is one that's really important, molecular size and the speed. If we're talking about a gas, how fast is that going? Well, we know what gas, the laws of gas state. The properties are its rapid movement, constant movement, random movement, and all collisions are perfectly elastic. That is the properties of a gas and the kinetic theory as it pertains to gas. So when we look at the Maxwell-Boltzmann molecular speed distribution, so let's look at what this is basically saying here. So we have the relative density on our y-axis, and we have the speed down here in meters per second. And then over here is our little key. So we have helium, neon, argon, and xenon. So if you have your periodic table and you grab it and you look at it, we have helium being very tiny. Its molar mass is 4. Neon is 20. Argon is basically 40. And then we have xenon, which is 131. Hopefully you remember the relative mass, the size is very important when it comes to the speed. So the larger, the slower the speed is going to be. That's a real key concept. And this Maxwell-Boltzmann distribution curve shows us that. So here we have our xenon. So our xenon is a big molecule. It's going to move relatively slow. So you can see that its distribution curve is not that big because the speed is slow, so you're not going to have that much on either side of that for as far as kinetic energy goes. The next one we have here is our argon, AR. Argon is smaller, so its speed is faster, so you see the curve is a little longer. So now you have kinetic energy average. Its speed is going to be a little bit quicker, so you're going to have on both sides of the average particles moving. You have the average velocity right there and there. So the next one we have here is neon. And right here you can see 500 meters per second basically as an average. So you have some that are going to be much more than that, some that are going to be much less than that. But that's your average. Why is the distribution larger? Because it is a smaller molecule. And we get to the smallest, at least on this list here, we have helium, and you notice that average is over 1,000, about 1,100, maybe just a little bit more meters per second. And when you talk about that, look at the distribution. So now you have a large range of speeds that are within it for the average to be that. So the lower the speed, the less the average. The greater the speed, the more the averages are that. The more that make up that average, I should say, the distribution spread is much larger. So please remember this. This is really good for speed, for kinetic energy. There's a lot of things that go into Maxwell-Boltzmann distribution curves. So types of solids, let's talk a little bit about types of solids. So we have molecular solids, and we know that there is properties that are associated. Molecular solids typically are going to be low melting points. They're going to be poor conductors of electric. They're softer. They're not going to be sonorous or anything like that. Then we have the network solids that are covalent, the network solids. Those, like a diamond, they're very strong. Buckminster fullerenes, any of those things, very high melting points, but typically still poor conductors. That's property of a molecular compound, poor conductors of electric and thermal heat. Then we have ionic. Now we know ionics are brittle. They will break if they're dropped or struck because of the ion formations, and you can rearrange them into positive on positive and get repulsion forces. They have high melting points, but they do not conduct electric unless they're molten or dissolved in water, and that is a property of an ionic compound. Then we have metallic. Metallic are good conductors. That's because of that sea of electrons. Remember, we talked about that previously. So they're malleable, they're ductile, they're good conductors, and they're solids that are very stable, so they have high melting points. So also there falls into solids some characteristic crystalline solids, amorphous, which has no internal structure, it's just random. So there's lots of other things, but these are basic characteristics. Here's giant lattices like sodium chloride, and we understand that in a solid, this is a great type of question you could get on some diagrams or explanation type questions. Why does a solid not conduct when you talk about an ionic solid when it's in its solid form? It's right there. The ions are not free to move. They're in that lattice. They're stuck in that lattice. Now, when it's melted or dissolved in water, now there is ability to flow, electron flow, and that's what happens. Ions form a regular pattern to the positive and negatives. We know that already. Remember, the unit cell is the smallest repeating geometric shape. Strong, high melting point, strong bond, and then they conduct electric. Typically, when you talk about a solid that is a molecular solid, they do not conduct, typically. Now, there's always exceptions. Silicone is a very good conductor for the most part, and that's why it's used in computers, so it's called a semiconductor. Heating ionic compounds. So let's talk a little bit about the high melting points and boiling points and the relationship to the charge. This is a nice chart here to talk to us about it. So here we have sodium chloride, and we know the sodium is +1, the chloride's -1. Here's our melting point, 800 degrees Celsius, and our boiling point really high up there. Look at magnesium oxide. Magnesium oxide. Magnesium is 2+ and oxide's 2-. So now you have a more charge, so you have more attraction. Please keep that in mind. It's a very important concept. Look at what happens. Look at the melting point. 2,852 degrees Celsius, and then the boiling point 3,600. So significantly increased because the charges increase. Larger, and this is a key concept right here, larger ionic charges produce stronger ionic bonds, so much more heat is required to break them. Keep that concept in mind. Here is another, just a little quick look at it. So you have NaCl, sodium chloride, and here you have sodium bromide, and relatively close when you talk about their lattice energy needed to break them. And then here you have calcium fluoride, so you have a 2+ now, and here you have 2+ and a 2-. So look at that. This is because this is just a 1+, so you do have a little bit less of a charge attraction because of that 1+. Look at the energy needed to break calcium fluoride. It's very high. But look at that 2+ and 2- held together. It's a lot more. It's basically almost 1,000 kilojoules per mole more. So the higher the charge, typically you're talking about stronger attraction, higher melting boiling point. Gases. We mentioned them before. Constant, rapid, random, perfectly elastic collisions. So the gas laws. So we are going to go through the gas laws in this section. So remember, we have Boyle's law, and Boyle's law is the inverse relationship between pressure and volume. Charles's law is the directly proportional relationship between volume and temperature, and Gay-Lussac's is pressure and temperature. Still a direct correlation, directly proportional. Then we have our combined gas law, where we have our pressure, volume, temperature equals our secondary pressure, volume, and temperature. And our ideal gas law. Please remember, the ideal gas law can be manipulated several different ways, and we've worked many problems in class like that. So let's take a look here. So remember a couple key points here. Your volumes can be in liters, it can be in centimeters cubed. Your pressure can be in atmospheres, it can be in kilopascals, it could be in torr. Your temperature must be in Kelvin. Please don't forget that. That's really important. When you come down here to our ideal gas law, if you look at your sheet, formula sheet, you are given the R constant for, let's see, you are given the R value for atmospheres, kilopascals, and torr. So you could have it in either one of those three. Either of those three would work in solving. So ideal gas. So let's talk about ideal gas. And we have the pressure, volume, the moles, and the temperature. And the temperature go up, the molecules move faster. Pressure is caused by them striking the walls. That's why if the temperature goes up, the pressure is going to go up unless there is a relationship of the volume that's thrown into the mix. But not all gases act ideally. And that is one of the things that is dealing with intermolecular attractions. And a lot of times a larger gas molecule, like a xenon or something like that, that's a larger molecule. If it's forced together under high pressure, so low temperatures and high pressure, you can get condensing to happen and it forms a liquid. And that is a deviation of the ideal gas law. It's not supposed to have any attraction. So those are deviations from ideal gas. And that's a key concept there. You could have maybe have to pick or write why that's happening. And it's the London dispersion forces that are working on a larger molecule under low temperature and high pressure. So when does a gas most act like ideal? Most act like ideal. And that would be high temperature and low pressure. That is when it acts most like an ideal gas. Deviations from an ideal gas, well, that is low temps and high pressure. Those are some key concepts. Most like ideal. You have that in your notes already, but it wouldn't hurt to get that down in again because that is a very important concept when it comes to gases. All right, now let us look at a couple of example problems. A weather balloon has a volume of 35 liters at sea level, 1 atmosphere. After the balloon is released, it rises to where the air pressure is 0.75 atmospheres. What will the new volume of the weather balloon be? Well, what we see happening here is this is a balloon and you have your pressure, you have your volume, and you have pressure. What you do not have related here to you is the temperature. So we're assuming that the temperature is insignificant as far as that goes. So we have pressure 1 over So pressure 1 times volume 1 times pressure 2 times volume 2. And this is all over T1 and T2. But we can say this is negligible because it's not given to us. So we can actually cross that out. So now we're just dealing with what's Boyle's law. So we can write down all our constants here. So P1, I like to write everything out if you remember from when we did this previously. So pressure 1 is 1.0 atmospheres. Volume 1 is 35 liters. Our pressure 2 is 0.75 atmospheres. And our volume 2 is blank liters. So we don't know what that is. So we could just basically rewrite this and set this up that we're solving for V2. So V2 equals P1 V1 over P2. And I just took this right here and I rewrote it right there. So now I can plug in everything that's given to me. So I have 1.0 atmospheres. I have my volume 1, which is 35 liters, and my pressure 2, which is 0.75 atmospheres. 0.75, the atmospheres cross off, and this is going to equal. So let me plug this in my calculator. So I have 35 divided by 0.75. So rounding to 2 significant figures, I have 47. So 47 liters. That is, and I can come here and write that, 47 liters is my volume, my secondary volume. So that's our first example problem. All right, so here we have our next, an airtight container with a volume of 4.25 times 10 to the 10, internal pressure of 1 atmosphere, and 10 to the 4, sorry, my bad, an internal pressure of 1 atmosphere and an internal temperature of 15 degrees Celsius is washed off the deck of a ship and sinks to the depths where the pressure is 175 atmospheres, so tremendous amount of pressure, and the temperature is 3 degrees Celsius. What will the volume of the gas be when the container breaks under the pressure at the depth? So that is telling you that's when it's going to break at this specific information. So if you notice, you have pressure, you have volume, you have temperature. So you have the combined gas law here. So I'm just going to come over here and I'm going to write down P1 V1 over T1 equals P2 V2 over T2. And I am going to write down everything that I am given. So I have P1 V1 T1, P2 V2 T2. I'm going to come in and fill in all my information. So it says here that an airtight container has a volume. So my initial volume is 4.25 times 10 to the 4th liters. It says my initial pressure is 1.00 atmospheres. Then it says here that my initial temperature is 15 degrees Celsius. So 15 degrees Celsius equals. So I got to convert that to Kelvin. So I go my 273 plus my 15. So I have 288 Kelvin. So I have 288 Kelvin. So the next thing I have here is my pressure 2. So it says here my pressure 2 is 175 atmospheres. it's my volume is what I'm solving for right here. And then it is my temperature is now 3 degrees. So 3 degrees Celsius. So that's equal to 276 Kelvin. So I can just go ahead and convert this whole formula right here. So I can just write it out as I'm solving for what will be the volume when this thing breaks. So I have V2 equals my P1, V1, T2 divided by T1, P2. All I did was just rearrange this formula right there. So now I can plug all this in. So I have, and I like to write all my units and everything. So I have 1.00 atmospheres. I have my 4.25 times 10 to the 4th liters. I have my T2, which is 276 Kelvin. My temperature 1, which is 288 Kelvin. And then my pressure 2, which is 175 atmospheres. My atmospheres cancel, my kelvins cancel, and now that just leaves me the opportunity to plug all this in. And when I look at this, I have to round to 3 significant figures, 3 significant figures. So let me plug all this in. So I have and I'm going to divide that by times 175. And I should come out to my volume 2. If I round it to 3 significant figures, I get 232.7. So 233 liters. So at that point, it bursts. All right, so let's look at another example problem here. So 2 flasks are connected with a stopcock, and we have flask number 1 has a volume of 2.5 liters and contains oxygen gas at a pressure of 0.70 atmospheres. Flask 2 has a volume of 3.8 liter and contains hydrogen gas at a pressure of 1.2 atmosphere. When the stopcocks between the 2 flasks is open and the gases mix, what will be the resulting pressure of the gas mixture? Think about this for a second and pause the video and give it a whirl. Run with it yourself and see what you come up with. All right, hopefully you took a moment to try and solve for this. Hopefully you realize that you have 2 different gases, you have volumes. So you're gonna have to split this up. And first, I'm just gonna put that we're gonna solve for oxygen here, and we're gonna solve for hydrogen down here. And then it's asking for the total pressure. So we're gonna have to find pressure total at the end. So we have several steps to try and solve. Noticing that there is no temperature, so the temperature is held constant. So we are using Boyle's law again. So we have P1 V1 equals P2 V2. All right. So let us look at, we're trying to solve here for our second pressure after we have opened the stopcock. So I'm going to rewrite this here as P2 equals P1 V1 over my V2. So when I look at what is given to me here, my pressure 1 is 0.70 atmospheres. says my volume one is, it says it is a 2.5 liters, so 2.5 liters. And I'm solving for the pressure 2 for oxygen, but if you look at what is volume 2, the 2 flasks are opened, so I have to add these 2 together to get my volume 2. So that's going to come out to 6.3 liters. So now I can plug all this in and calculate my pressure, secondary pressure of oxygen. So I have 0.70 atmospheres. I have 2.5 liters. And I'm going to divide that by the total, the new volume is 6.3 liters. So if I plug that into my calculator, I get 0.70 times my 2.5, and I'm going to divide that by 6.3. So I need to round to 2 significant figures, and I get 0.2777, so that's going to be 0.28. So pressure 2 of oxygen is going to equal 0.28 atmospheres. I'm going to circle that right here. Now I'm going to come back and do the same thing over here for hydrogen. So I'm going to rewrite everything here. P1 V1 equals P2 V2. I have my pressure 1 is, in this case here, 1.25 atmospheres. My volume 1 equals 3.8 liters. And my volume 2 is going to be the same because I'm adding them together. So this is 6.3 liters. So now I can solve. So I can go, my P2 here for hydrogen equals P1 V1 over V2. So plugging in now, I have 1.25 atmospheres. I have 3.8 liters, and I'm going to divide that by 6.3 liters. So my pressure 2, and this is hydrogen, is going to equal, let me plug this in. So I have 1.25 times 3.8 divided by 6.3, and I have to round once again to 2 significant figures here, and I'm going to get 0.753, so that's going to be 0.75. So 0.75 atmospheres. So the total pressure is the sum of all the partial pressures. So I'm going to have pressure total equals pressure of O2 plus pressure of H2. So if I look at here to plug this in, I have 0.28 atmospheres plus 0.75 atmospheres. So my pressure total equals. So once I open the stopcock and allow the gases to move across, 0.28 plus 0.75. So I am going to have, I have to round at and keep at 2 because I'm adding 2 decimal places. So I have 1.03 atmospheres. And that is my pressure total. And let's see here, we have one more. How many moles of gas occupy? So let's look at here. How many moles of gas occupy 98 liters at a pressure of 2.8 atmosphere and a temperature of 292 Kelvin? So we don't have to do any conversions. So this is my ideal gas law. So I can come here and I can write PV equals nRT. And I'm in atmospheres right here, so that's going to be my R is going to equal, if I grab my sheet, that is going to be 0.08206. 0.08206. And that is liters times atmospheres over moles times Kelvin. All right, so we're going to solve for moles here. So I'm just going to redo this formula real quick, and I'm going to go N equals, and I'm going to have PV over RT. So my pressure is given to me, so I have 2.8 atmospheres. My volume is 98 liters. My R value is 0.08206, and this is liters times atmospheres over moles times Kelvin. So that's here in parentheses, and then lastly is my temperature, which is given to me as 292 Kelvin, 292 Kelvin. So cancel, 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 and I am just down to moles now. And this here, let me plug this all in. So I have 2.8 times 98, and I'm going to divide that by parentheses 0.08206 times 292. So I need to round to two significant figures since I have only 2 and 2 here. So I have 11.45. So rounding equals 11 moles. So that is using my ideal gas law. Remember, the ideal gas law can be manipulated in many different ways. So that's just the beginning part. We are halfway through the key concepts of Unit 3. So my next virtual lesson will pick up right here and begin moving forward with solution chemistry molarity. Thank you for watching. Have a good day.